Hey, welcome back. Let's kick things off with depth-first traversal of a graph. So just like with trees, which we spent a good amount of time on, binary search trees or binary trees in general, there are two main options for traversing these trees, depth-first and breadth-first traversal. Now within depth-first, we did talk about pre-order, post-order, in-order, but the general idea behind depth and breadth-first is what we care about. So when we say depth-first for this binary search tree, or any tree, it means that we're prioritizing visiting children of a given node before we visit siblings. Or we deepen the traversal before we widen it. So what that really means, whether we're going left or right first, doesn't really matter. But let's say that we go left. So we start at 41, we're going to visit 20. And rather than going to the sibling, we're now going to finish out the children of 20. So that gets us to 11, it's a dead end. Go back to 20, finish out the children, now we hit a dead end. Now we go back and visit 20's sibling. And then we keep doing that. So we prioritize deepening of the traversal rather than broadening, rather than widening. So that's depth first. But in this section, we're talking about graphs that are not trees. And they're not necessarily harder to traverse, but sometimes it can be a little trickier to understand what depth means versus breadth. Because it's easy on a tree where we have a clear direction down, or it depends, how it's drawn. Sometimes you see trees drawn upwards from the root, but however it's drawn, there's a clear path through that tree. There's one root, and then you descend away, or you ascend away, or whatever it is, you're moving away from that root. So depth first means moving away from the root. When we talk about a graph, a more general graph like this, and this is a directed graph, unfortunately this website doesn't let me do undirected graphs and traverse them, but anyway, let's say that we pick one of these vertices. There is no root node like there is on a tree, but let's say we're going to start at 0. What does it mean to do depth first traversal from here? Well, really all that it means is finding one neighbor, following one neighbor, let's say 1, but there's actually 3 neighbors. We have 6 and 2. Let's say we follow 1, and then we continue to follow the neighbors of 1 before we visit its siblings. And when we say siblings, it's kind of different than a tree because they're not necessarily on the same level. But let me just put it this way. If we start at 0, let's say that we always choose the lowest number as our next item to visit. So we go to 0 to 1. Now in a breadth first, which we'll come back to, we would then visit the other neighbors of 0, like 2 and 6. But in depth first, we're going to go 0 to 1 to 5, and then come back to 1 and go to 6. And then from 6, we visit its neighbors, like 7, and then 9, and so on. Rather than a breadth first, where we're going to visit 0, 1, 2, 6, all of 0's neighbors first before we visit 1's neighbors and 2's neighbors, and so on. So let me show you a little animated diagram I put together. Here's a simpler graph. There is no, root node that we start from by default, but let's say we're doing a depth first traversal starting from A. We want to explore as far as possible down one branch before we backtrack. Again, we have to decide the order we're going to visit things in. So if we have A, there's 2 neighbors. Which one do we visit first? Well, let's just go with alphabetical order to keep it consistent. These are both neighbors, and we could visit either one first. But let's say we're going to visit alphabetically, so we start from A, and then we visit B. Now, if this were breadth first, we would then go back to A and visit E. But depth first means we're now going to explore B's neighbors. So let's pick a neighbor. Alphabetically first, we have C. We could do D, but let's do C to be consistent. Now from C, we have 2 neighbors. And we've already visited B, so this is an important idea. We have to remember where we've been. Otherwise, we could just go back to B. So we've done B, so that leaves us D. Now from D, we have 2 choices. And if we're going alphabetically, we're going to go to E and then to F. Now that order doesn't really matter as far as depth first. These are both neighbors to D, but it's just helpful for us to kind of have a concrete order if we're just doing alphabetical. Okay, so it's really important that we remember where we've been. Otherwise, we would go from A, let's say we go to B again. Well, B has 2 neighbors, or 3 neighbors, C, D, and A. And if we don't remember we've already been to A, what's stopping us from just going back to A and then going back to B? If we're always picking the earliest alphabetical, the lowest alphabet, A and then B, we'd get stuck. So here's another example. A slightly different graph. I know it's the same nodes, the same vertices, but different edges. If we start from A again, if we're doing lowest alphabetically, we would go to B. And then from B, we only have one choice. We go to D. Now we have two choices. Which one do we go to? Well, if we're doing alphabetically first, we go to E. Now we have two choices. There are three edges, but we know we've already been to D. So do we go to C or F? Well, if we're doing it alphabetically, we go to C. Now, from C, it's a dead end. We visited A, we visited E, so we go back to E. And now we have to finish E. We have F. And then we're done. So here's one more. It's the exact same graph, actually, same animation, but down here, I'm displaying our adjacency list. So you can see A is connected to B and C, and that's reflected here. And I do have things listed alphabetically first. So the edge from A to B comes before A to C. Again, it doesn't really matter, but for me to explain, it's easier to do alphabetically first. Okay, so if we look at what happens from A, we start at A, and we visited A. So we're going to cross it off, meaning that anytime we see A as a adjacent node, we're going to ignore it. So we look at A, and we see that there's two edges, two vertices. So we could go to B or C, and we'll just take the first one. We go to B. So when we visit B, we now cross B off from here and from here to all of its edges. This doesn't mean deleting them. It just means that we're going to remember, I've already been to B, so ignore it next time we see it. So we get to B, which is right here, and we see that it has two edges, A and D, but we've already been to A, we cross that off. So now we go to D, and we cross D off because we've been there. It has three edges. We cross D everywhere. So now at D, we look, well, there's three choices, but we've already been to B, so we'll go to E next. And we cross off all those E's. Now we go to E. Where should we go from E? Well, let's go to C. Okay, so we go to C, and we cross all those C's off. And now we go back to E where we were last, and we've already visited C, we've already visited D, now we need to visit F. And we're done. Okay. So that's the basic idea of depth-first traversal. We follow a branch down. It's harder to say we're deepening because it's a little more challenging to visually understand what depth means in a graph. Because when we have a tree, it's easier. We're moving away from the root. In this case, this looks like a loop basically. So depth is harder to explain. What it really means is just following the neighbors and continuing to follow neighbors before backtracking. So we're going to implement depth-first search both recursively. Oh, I said search. We're actually going to do traversal. It's the same idea, except we're not searching for something. We're just going to visit every node, every vertex. Anyway, we're going to do it recursively and iteratively, just to show you both approaches. It's a good thing to know. So we'll start with the recursive solution. Well, first the pseudocode in the next video, and then an implementation afterwards, and then we'll do it iteratively, and then we'll cover breadth first. Okay.